Hi everyone, today I'll be talking about the cyclomatic complexity. It's a very useful metric, not only to measure, of course, what the name is already saying, which is how complex is the code, but it's more than that, it can help you to estimate the number of unit tests that we need. And this is quite important, and I can tell you a story about that it's true, and it's quite recent. It's quite recent on my professional life. In the company that I work on, we inherit a specific project and we find out that the code doesn't have any kind of unit tests. And at some point in the meeting, someone asked me, okay, how much time do we need to develop some unit tests? At least, let's say 70% of coverage to make sure that not only the code is reliable, but more than that, when you start to develop unit tests, you start to understand how the code works, and maybe you have to refactor the code. It's a quite challenge, but at the same time, it's a way for you when you narrate the code and you have time to understand it better, the code, you can fix some of the issues that you find, and at the same time, you can improve the code and make it more your way, let's say like this. But as I was saying, someone asked, okay, how much time do we need to develop unit tests? And the time was important, not only because we want to release the product, but at least with some quality and we can trust somehow how the application is developed and the quality of the application. But of course, we need to understand how much it costs because it's a technical debt. And imagine that if you need 3 months or 4 months to develop all unit tests, of course, it will be 3 or 4 months of the salary of someone. And it's not only that. Sometimes people think that the problem is that we spend 4 months developing, so we are losing this money somehow. But the problem, it's not like that. There's a kind of a thing that, and I will create in my series about decision frameworks, that it's called opportunity cost, which means that for one side, you will spend time developing the unit tests, so it's a technical debt. But from the other side, you have a developer that could be doing something that will be profitable to your company. So you are losing money because you have to pay this technical debt, and you are possibly losing other money during these 3 or 4 months that you could use to create a product with the time of this person. So sometimes people, okay, now you just lose 4 months of the salary of the person. But it's not, it's more than that. It's these 4 months plus the value that you could profit if you were using this person to develop a different product or doing anything else. It's called opportunity cost, and I already created a video. I didn't publish it yet. Maybe you want to check, because sometimes we see the value that we are spending in something, but we are forgetting what could we have done with that time to do other things. That it's also money that we are not receiving because we choose another option. That it's called cost of opportunity. So why is this important? So one of the ways, and it was very difficult to find out, is, okay, how much time do we need to develop these unit tests? And people will say, hey, for my experience, 2 months, 3 months, 4 months, and so on. And as an architect there, I say, okay, it's usually my job to try to coach people, wait for them to bring their ideas, to do some brainstorm, and help them to understand how to look into these things. And I say to them, okay, maybe you should think about the cyclomatic complexity, because the cyclomatic complexity measures, and I will go into detail in a moment, for instance, the number of paths that the code contains. So meaning that usually when you are doing the unit tests, and if you are an experienced developer, you're developing unit tests, you know that you usually look into a method and you try to find conditions. So you want to make sure that the code is tested in one of the paths. Then you find out that there is a condition point, like an if, and you say, okay, what makes this if true? What makes this false? So I will need two different unit tests. And the cyclomatic complexity measures these things. So somehow you can take the value returned by the cyclomatic complexity and as a basis for you to guess how many unit tests do we need. Of course, it doesn't mean that you can guess the time. For that, probably you need, on average, the number of lines of the code for each method, on average, what is the cyclomatic complexity of the methods, and then you have to ask to a trustable developer. And I say trustable is not they are lying, but someone that it's really, that really gives you the truth, even if you don't like, and say, okay, I need 3 hours for each unit test or 2 hours. And then you can multiply for all the values that return by cyclomatic complexity. And if you want 70%, you multiply by 0.7. and you have somehow an idea, a measure. It's a measure. It's not a 100% reliable one, but I would say maybe 70-80% you can trust on it, and you have, let's say, a number that you can present with the facts, with math that you can present to the manager and say, I will need a person for 3 months to develop these unit tests. And then you can use, for instance, again, the opportunity of cost. Okay, but during these 3 months, should we give to this person another job that can make us more profitable, things like that? But that will be a management decision. But you have a way to provide value, real money value to the management as a technical person. That's when when you understand all these metrics and what they represent, you can make these things. And if you follow my channel, it's about architecture. I have a lot of videos how to be an architect, and I provide a lot of different angles about different subjects. Sometimes people don't understand. They expect only system design and architectures and patterns. But more than that, that's what I try to pass on these videos, for you to understand what it's behind, because it will make you more professional, and it will, let's say, help you to advance in your career, your professionalism, and things like that. That's why if you look into my videos, you will see that this is what I'm trying to push. Because if you want to see how a pattern works, you can go to the internet and you can see how it works. But I like to provide the value behind it. And that's what I want to provide here. It's for you first to understand what is cyclomatic complexity. Even if it's the first time that you are hearing about this metric, you already somehow know what I will be talking about. But of course, I will go into details and explain in detail everything that I said here. So let's start. So what is cyclomatic complexity? Cyclomatic complexity is a software metric used to measure the complexity of a program. And it's important to measure the complexity of a program for a lot of reasons. And one of them, it's one that I explained earlier about the number of paths. It was defined by Thomas McCabe. In this year, you can see from this year that there was no Java and other language that you are probably using, but it can still be applied with high reliability. It represents the number of linear independent paths. That's how you measure complexity. It's when you have a lot of options. At the end of the day, it's how many options do you have in your program when you follow the code. Okay. So the form is usually, it's like this. So cyclomatic complexity, it's the number of edge. If you draw a kind of a workflow from your code, it's the number of edge, which is these arrows here, minus the number of nodes, which is these guys here, plus 2 times p, and p it's the number of components. In this time, there were no classes and things like that. At least it was not popular, object-oriented. So there was a kind of a programs, and usually the formula says, okay, then you add 2 plus the number of connected programs. For instance, if you use COBOL, and maybe I'm wrong here, I'm not experienced in COBOL, but I remember that they are files that you can call, they call it programs and things like that. And you have a program, then it can call another program. It's not methods calling methods. And that's from this time, but you can apply this, you can call it a program, your application, your SDK, your jar, or something like that. Usually you will use one when you are analyzing a project. But if there are relations and you are measuring 2 at a time, maybe you can use 2, and then it's 2 plus 2, it will be 4. So this number starts to increment. But remember that this number is not multiplying the result of here. It's not like you have the number of edges and nodes from one program, and at the same time you have the other one and you are multiplying. That's not, it's just a plus here. So it doesn't have a big impact even if you do a mistake. And at the end of the day, you don't have to use it. This formula is usually, you have a lot of tools that use this formula for you. The idea is for you to understand how this works. So again, so you have this formula, cyclomatic complexity, it's the number of edges minus the number of nodes and plus this. For instance, in this one, let's see an example. We have the number of edges, 1, 2, 3, 4, 5, 6. And the number of nodes, you have 1, 2, 3, 4, 5. So 6 minus 1, you can say that it's 1 plus 2, because p is just 1. So it gives you 3. And if you check here, we have one path. You go through the left, a second path here, and you have the third path. You can see that this formula somehow works. And it was a formula with almost 50 years. It's quite nice, right? So why this cyclomatic complexity matters? First, if you have higher complexity, it means that you have more paths to test. Because if you have a lot of paths, you have to test all of them. More maintenance effort, meaning that if you do a change in your code somehow, and you have to understand the impact. So here you have 3 possible results that reach the end of the method. Imagine you have changed to something in the A. It can have implications in 3 different paths. So it starts to be quite difficult to understand the code. That's why now you understand why it measures the complexity. Okay, and of course there will be a higher change of bugs. Okay, lower complexity, less paths on a method, so better readability and easier debug and testing because you need less tests and it should be easier to develop it. So how should you interpret? This is quite popular. I will not explain why, but I think intuitively you understand why. If you have a value per method, and I will be talking here per method, somehow let's target the method, not the class here. Between 1 and 10, it's simple low risk. I mean that 10, it means that your method should have 10 different paths. Sometimes they are not paths, they are statements. The way it is counted, maybe if you have 10, maybe the number of paths is between 7 and 8. It can happen, but it's a number that you can manage it. You look into the code and you can manage it. It's a condition if that has another condition and maybe a switch. I can understand this. But of course, you already saw code like me, that you have an if with another if that with a lot of ands and ors, things like that, and they start to be really complicated to understand. So simple low risk between 1 and 10, recommendation, it's the ideal point. If you start to be close to 20, it's moderate complexity, you should review, maybe you want to refactor that method if you are developing. Now, for instance, sometimes in legacy, and I really found sometimes I really find this kind of methods between 21 and 50. I already saw methods, and I'm not lying here. I'm saying truthfully, with a lot of times methods with 80 and 90 of complexity. People start to put an if and then inside other ifs and then another ifs, and no one wants to refactor that code. They understand, they put some comments, and they start to go deep and deeper with 5 and 6 deepness on or nested ifs. And it starts to be really, really crazy to read. Everyone is afraid to change that code. Okay, so usually you should target this value between 1 and 10. If you follow, for instance, SonarQube, which is a tool that you can use to measure if you're using Java, a lot of, not only Java, but a lot of languages, usually it starts to throw you a warning when you have, for instance, by default, I think it's 15, if I'm not, but you can change that. So cyclomatic complexity and unit testing, there's a great, of course, high correlation between them. So usually this is it's more or less, it's not accurate, but it's quite close. Minimum number of test cases needed for full branch coverage, which means that it's associated also with the coverage of your unit tests. The cyclomatic gives you the number of tests that you need, and of course, that implies that with another metric. So you can use lines of code to make better guesses, but if you want a real guess about the coverage of your tests, of course, the cyclomatic complexity has a high relation between the cyclomatic complexity of a method and the coverage of your tests, because it's the number of paths. Okay, this is just an example here. So it's easy, you have 3 paths. The cyclomatic complexity probably here will be depends on the code, maybe 3 or 4, but at the end of the day you need at least 3 tests because you want to test when A it's minus or equal to 0, the same for B, and otherwise we'll go to the third path here. It's quite intuitive to understand. So let's see an example in a more, let's say, scientific way. Imagine you have this function with this code, which is the same as this one, and you can draw it something like this. So you have the start, and you have this first condition. This is one node, this is an edge. And if this is false, you return 3, which is this one here. And if this is true, you should check now the B. And if it's true, you go to the 1, and then you finish, or you get to the 2, to the finish. And here on the 3, of course, it finished. And you can see this row. It's overlapping the other one. You can see that you don't have here an arrow. I should have put somehow around, but it's there is a path here. Okay, here you have 2 paths, but it's not this return 3. It's not connected to return 1, of course. It's connected to this. And so the number of nodes you can find in 2 ways, and I'm showing you here 2 ways to do it. Usually you can target this 5 because it's your code. 1, 2, 3, 4, 5. But most of the time in some tools they will give you 7. They will count the start and the end, and it's quite common for you to see this, which means when you are counting the edge, you follow the same logic. So you have an edge here, and you have the edges from these returns to the end. Usually you should have almost of the time the edge bigger than the number of the nodes. So you can have 5 nodes or 7 if you count start and end, and you have 6 edges, 1, 2, 3, 4, 5 and 6 with this one here, or 8 if you count again the connection to here. Okay, so but in both cases you will receive always 3 here, and maybe you can even find maybe 5, 7, 6. Yeah, usually you can see both. I was thinking about if I have found out another tool that gives you a different approach to this calculation. It depends, but I will talk to you in a moment, because there is something called cognitive complexity that I will explain in a moment. So the number of nodes, it's 5, and you can see all of them. It's your code, the conditions, and the return. Okay, these are the 5 nodes, but of course you can also have one entry and exit, and then you have 7 rather than 5. And the edge, it's explanation. So that's the connections between the entry and the first condition here. Then we have this when it's true, and of course this is when it's true, this is when it's false. Then we have the B when it's true and the B when it's false, if you put it like this. And each return leads to an implicit exit. And you can have again 6 or 7 or even 8, depends on how you see it start and the end. But at the end of the day, what matters are these ones, the really connections between the nodes of your code. Okay? The idea is for you to understand the paths, the formulas. Sometimes it's applied in a different way. And I'm saying that because sometimes people say, okay, but what is the real formula? Remember that this formula was invented 50 years ago. No one changed the formula. So it's a kind of a guideline. But at the end of the day, even after 50 years, it's quite reliable, and usually it gives you a very close number to the real number of paths in your code, because it uses graph theory, it uses the edges and numbers. But it depends what do you consider for the complexity, the node and the edge. And if you take all the ifs and things like that, that will give you a number. If you consider that the return at the end, even if it's not written, it's it depends on the language, it's the latest statement and the start of the method also you add 2. But at the end of the day, it doesn't matter. These small changes, it will not have big implications in your decisions. Because if you have a complexity cyclomatic of 200, no one's cared if it's plus or minus 3 or 4, depending how you are counting things. Okay, so the formula again, it's like this: 6 minus 5, and the P it's 1, and again 3, and you can check using this formula. And if you use these numbers, you have 3 paths. Like again, you have 1 that goes through here, 2 and 3. That's what it's the most value here on this metric. So implications, testing and coverage, as I was saying. So 3 linear independent paths, this one, and this one here. So you need at least 3 unit tests required for full branch coverage. So there is a very strong relation between, of course, the cyclomatic complexity and the number of unit tests, implicitly, of course, the metric coverage. So related metrics, and I put them here, you have lines of code, often correlates with CC, but not always, meaning that if you have a lot of lines of code imagined per method, of course, there is a high probability to have more complexity. It's not always the case, but usually there is association. Why it's interesting for you to know about this, and you can check my previous video at lines of code. If you have bigger methods, and probably there is a high again probability of the cyclomatic complexity is bigger, but at the same time maybe you want to refactor them. Maybe it should be if you have let's say I have a higher I have methods with 100 lines of code. Even if the complexity it's not high, maybe you should take them to refactor and reduce number of lines, because later any changes on this code can have big implications on the complexity, and it can rapidly grows this complexity. So be careful of that. Usually I would say a number between 30 rows per method, it's quite okay, maybe 40 maximum. After that, refactor the method, split into methods. It will be easier, and I'm sure that you can control later better the cyclomatic complexity. Code coverage, of course, because code coverage is related with tests is related with paths, and paths it's quite related with the cyclomatic complexity. And there is another one that I will talk in a moment called cognitive complexity. It focuses on understandability. It complements the cyclomatic. It's not cognitive, it's cyclomatic complexity for readability analysis. They are very similar. They measure not the same thing, but of course the concept of the complexity, it's there. So what is the cognitive complexity? It was introduced by Sonner Source to address the limitations of the cyclomatic complexity. What is the limitation about the cyclomatic complexity? Because the idea of the cyclomatic complexity is to measure the paths, but that sometimes you have multiple paths, but they are readable by human. You have good variable numbers and you say, okay, maybe I have these conditions and I can understand what's happening here. But sometimes you have just two paths, but you have a lot of ends in the expression of the if, and for a human it's difficult to read. It's easy to make the test, but it's difficult for a human to read. So it's cognitively, I don't know if I'd say it correctly, human difficult to understand. Okay, so it measures how difficult a function is to read, reason about, and mentally simulate. It's difficult in our mind to understand the code, and we are afraid to change it. And even if the cyclomatic complexity is slow, if you put a lot of ands like this in the conditions, it starts to be difficult to read even with just one if. If I bigger than 7 and b less than 3, and you say, what is this 7, what is this 3, why this and what happens when it's bigger, and in our mind there are already 4 cases. But since it's an and, there is only 2 paths, and maybe sometimes the cyclomatic complexity will say, okay, just the cyclomatic complexity it's 2, but for a human it's not 2. We start to think in all the branches, and that can be difficult, and that's what the cognitive complexity measures, because it takes into account the nexting level. Because if you have an if inside another if, which by the way it's inside another if, like the example we had before, maybe you have a cyclomatic complexity of 3 or 4. But for a human, it's very difficult because, okay, when it's true, it goes to this one. And then if it's true, it goes to this one. But it's false, it doesn't go to the third one, but it's still inside of the first. And it's very difficult in our mind to create a kind of a mapping of the path. So there is somehow a reason to create a parallel metric called cognitive complexity that say, okay, from the testing point of view, it's easy to implement unit tests here. It's only 2 paths. But from a human point of view, it's quite difficult. Meaning if this project is being developed by a lot of people and there is let's say, a big rotation of developers, I want the code to be readable. So for me, it will be more interesting, the cognitive complexity over the other one. The other one, it will be good to test to make sure that I know how many tests do I need, but I want to use cognitive complexity using this context. Maybe it's not an issue and say, okay, now it's a very stable project. It's not relevant to cognitive complexity, but I think we should work with both. So it's the nexting level, the logical operators, the recursion, when you have a method that calls itself. From the point of view of tests, they doesn't make any difference, just testing the method. But from the point of view, I know a lot of people, they have a lot of difficulty to understand recursion in development. So loops, early exits, broke, continue, returns, flow break structures like goto, some also language, they use goto, exception handling, it's also return. So this cognitive complexity takes into account all of these things that create branches in our mind. So ignore structure that's familiar or readable like if, else, and shallow depth. So key difference, the cyclomatic complexity treats all control flow equal. So 1 point for each if, for, case, and so on. That's how the cyclomatic complexity it's calculated, for instance, from SonarQube. That's where you have a node for a complete if. They don't care if there are 2 or 3 ends inside. But the cognitive takes that into account. So that formula about the nodes, you can still use the nodes, but sometimes the value will not be 1. Sometimes will be more than 1. So let's see an example. Here you can see that you have 1 node, 2nd node, and the 3rd node. So you will have a kind of a 3 for the cyclomatic complexity, more or less. Intuitively, maybe 3 or 4. But if you go with the cognitive, since this if it's nested on this one, I should add or not. So this node will value 2 and not 1. And this one will value another 1. Because it's nested, so it's 1 plus 1. But since there is a boolean here, I will add another one, because if you with this, and because this if it's inside this one and we have these booleans, I'm sure that you understand it's more difficult for a human than for a machine. So the cognitive complexity here will be at least 6, while the other one will be something like 3 or 4, something like that. So you will need 1, 2, 3 tests to test this, because this is an AND. You just need the false here. The other ones will be true. So you need 3 tests to cover this. But the human, in his mind, needs more than 3 tests or 3 paths in the memory, because he starts to think what happens when this is true, 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 false, false, true, both false, and things like that. And we want to understand what is this D, and we always have this hand. It's like as if you have another if here inside this if, because of this and. Okay, so complexity scores usually it will be around 4, as I said, and cognitive about 6, because of these nested things that we have here. Why such a big gap? Because for a cyclomatic is just 1, but this B, since it's inside this one, it will be 1 for the structure and 1 for the nesting. And the same for this one, 1 for the structure, 2 for the nesting, here plus the Boolean logic. So that's why it's 6, and you understand why there is this big difference, because technically the cyclomatic I just need 4 tests, but as a human I need more than that to understand the code. Of course, you will use these values in different contexts. Again, you need one of them for the tests and the other one for the people that work in your code. If you are juniors, probably people that are juniors developers, maybe you want to take into consideration seriously the cognitive metric. That's one of the things that if you are senior people, okay, there is some relevance, but okay, you know that they can handle this. Maybe they can even refactor the code. But if you have juniors, you don't want this metric to go with very big values. You want to control these values because you want the code to be simpler, to be manageable and understood quite easily, even for people that are starting to develop, or they have, let's say, just 1 year experience or something similar. So the cyclomatic complexity, again, you have these 3 nodes here. So using the formula here, you have the 3 edges, 1 node probably, or 3 nodes and edges. At the end of the day, okay, 3 paths, that's more accurate, saying like this, and that value that you have at the end. Takeaway: cognitive complexity exposes mental effort. The name is already saying the cyclomatic focus on path count. Okay, it's completely different. They are both about complexity, but one it's more human oriented, the other it's technical oriented. So human readers care about nesting and logic, that what does make us difficult to understand the code. Test planners, people that for the quality they just care about the paths, because they are the options that can be taken by the code when it's running. Okay, but you should use both as a manager, software engineering, team leader, architect, to take good decisions, because at the end of the day, as I usually say, being a great professional in the IT environment is 50% technical and 50% about reasoning, management, and understand the stakeholders, understand the people, the technologies you have, and for that you should use numbers, facts, and you take decisions from there. And I really hope that this video can clear this for you, as my other videos if you look into my channel. But you should use both for maintainability. The cyclomatic tells you how much logic needs to be tested, again, and the cognitive tells you how hard it will be to read and understand that logic. Okay, it's what I was really saying, but I really want for this to be, let's say, stamp on your mind. A function can have low CC, okay, low. It's let's say it's not complex, but still be hard to understand. There are really creative people. I don't know if you already work with these people. I have really worked with people, even simple things. Sometimes they can be really creative. They go through all the functions, to the functional paradigm with a lot of lambdas and things like that. So the code, it's quite simple, just a few lines, but you have to look for a while to understand that. People really like, sometimes they really take proud on how they develop the code and how complicated the code is. I prefer, as usually, as a kind of a technical manager, people that write it simple language so everyone understands, because it will be a really strong factor for the success of the project. But at the end of the day, use both to decide when and how to refactor. That's one of the things that I usually use, these kind of metrics. So refactoring to reduce CC, one way to refactor, and I will show you how can I usually refactor. These are a lot of different strategies, and I will talk in other videos, but today I just like to show you a simpler one so you have an idea how to move on. Of course, just to give you a kind of an interest to this kind of thinking. So sometimes you should break large functions into smaller ones. Sometimes just split the code. Because if you have a code with a complexity of, let's say, 20, and sometimes you can take parts of that code and put in another method. And the complexity of that method will be reduced, and you move into another place. You say, but the complexity is the same. It is, but if you now you can test the methods separately, and it will be easier because you can mock methods. So you don't have to test everything together. So the number of paths in a method will not be 20, maybe it will be 15. And the other one that's 5, and you can test those 5, and then you test the others. You just mock the method method 2 that you created on the on method 1, and it will be easier. It's just a trick that you can do. It seems that you are cheating on this. Say, okay, but it's a trick. It is, but remember that it's about the paths and how you understand the code. Because the code it's working, probably, but you want to make it readable. You want to make it easier to test. It's the same code, but you can use these tricks to create more modular code to do this. So remove nested conditionals. Sometimes I just put these conditions in a method and call that method. And then from there, I try to see what can I do. Use polymorphism or state machines. Polymorphism reduce, for instance, switch. That's one of the patterns that sometimes when you try to understand how to refactor code, the usual switch became, or if a lot of, let's say a chain of each will be, sometimes you can change or move to polymorphism in object-oriented or state machines and apply design patterns for instance strategy. It's a good one or even common. Let's see how can you use for instance strategy. If you don't know the strategy pattern, please read it. I'm creating a set of videos of this about patterns. I didn't reach yet the strategy, but the strategy is a way that imagine that you have I'll give a simple example. Imagine that you in your code you want to use 3 different types of sorting, like bubble sort, quick sort, and shell sort. The parameters are the same. Usually you can do something like if the option is 1, I'll go quick sort. If it's 2, I'll go shell sort, and if it's 3, it will bubble sort. Or you can just create 3 classes that one of them implements the sort for quick sort, the other one for shell sort, and the other one for the other. And then you just, rather than using an if, you put that on a map and you get the value. So you remove completely the ifs and you just use the class based on a map. Or maybe you can just create objects like the strategy pattern by implementing an interface or abstract class, and you implement in 3 different childs, and you create a class called sortable something. And sometimes you create an instance of the bubble sort or the other, you just switch and call the sort. It's the full polymorphism. It depends how you apply the strategy pattern, but at the end of the day, it's just you can decouple your behavior. It's like as if you have a car. Outside it's the same, but you can change the engine inside for another one. But the car, it's the same. You don't have to do conditions, you just exchange. But let's see an example. Imagine that you have this type 1, do something A, type 2, something B. This is a quite common, really common pattern in these cases. And you have a complexity of forming. You have to test when it's 1, when it's 2, when it's 3, and make sure that you are calling these methods. Okay. So the problem, it's high CC in one function. Of course, it's not for that it's high, just an example, but it can contribute for that. It's harder to read and test if you have 7 or 8 or 9. It starts to be tricky. And if you have something more here on an if, it can be really difficult to read. And any change to behavior requires modifying this method. If something changed on the A, B, C, and needs a parameter, you have to go to this method, so it's really prone to errors. But you can refactor something like this. You create using strategy pattern. This class here, do something. You create a class for this one that implements an interface, like this one, interface strategy, with a method, for instance, called execute. And in this case, you just create 3 different classes. The 1 is associated with strategy A, the 2 the same, the 3 the same. And now you have the strategy, and you get based on the value that you receive, and you just execute it. And if you look into this code, it's doing the same thing as this one, but without ifs, which means that you reduce the complexity probably to just 2. Of course, here you don't see a bigger impact, but you have 10 conditions here. This will be 10 here, and here will still be 2. which is a great thing because it's quite readable. You understand the option 1, it's this one, the 2, it's this, the 3, that, and you just get, and you don't have conditions here. Because if you test, the only thing that you have to test, there is nothing. If this method is called for a value, and you want to make sure that if this is a parameter of a method, that the parameter, it's the parameter of this get, and everything else, it's already tested. You don't want to test the map because the map is already tested by Oracle. Okay, so one map lookup and one method call. And each strategy class, it has its own CC. Now you want to do some complexity analysis on each one of these classes, but that's in a different file. So you reduce locally the complexity of a method. So refactoring strategy doesn't remove the decision, just encapsulate it, just, let's say, simplify the problem. You spread the problem for different methods which are simpler to test. That's the main idea of this kind of refactor. You can use strategy, you can use comment, and of course this is just for this example. Of course there are other examples. Sometimes I move some ifs to lambda functions, and I test the lambda function. I'll reduce completely the complexity of a condition, let's say a conditional lambda function, and you just use that one. Trade-offs, of course, now before and after use strategy pattern or the other mechanism. You have one or plus the branches. Imagine that you have 10 conditions, you'll have a CC of 11. Usually it will always be 2. It will start to be, as if you start to add more conditions here, of course it will increment the number of tests and how difficult it is to test. Okay, here it's always the same, because the only thing that you'll be testing each one of these, because this code is always the same. Okay. And extensibility, this is poor, this is great. You just create a new class and put on the map. Okay. And readability, I think it's quite easy to read this. Just, of course, not with this name, maybe it's options for something, sorting options or things like that, and just head here and you just read it and you get and you execute. It's really simple. So what is the ideal threshold? Just to remember, usually C plus 10, you should start to wonder what's happening. Fail if it's more than 20. Just fail the pipeline and make sure, or at least make sure that on the peer reviews you don't have methods, unless you have legacy methods, but in those cases you should create a task on your backlog as a technical debt or in the future to fix it. Misconceptions about CC. Low CC, it doesn't mean good code. You can still write really creative code. And if you want to know more about this, I don't know if you can find on the internet, but when I started to develop, there was a kind of context in the world called obscure C, which is the smallest code possible. How much can you implement something? And and it's about this. So low CC, it doesn't mean good code. It was a really complex code, but can do a lot with that. Kudos to the guys. High CC, it doesn't mean that it's bad code. Sometimes it's really well structured, just big. Sometimes you have condition if, then a great comments, then another block with ifs. Of course, when you look into this code, you say, I can split this in several methods and I will call these methods. That's right, but sometimes it happens in legacy code. But at the end of the day, you just say, okay, there is a 30 cyclomatic complexity, so this code is really bad. Now look into it. Sometimes it's not bad, it's just big. In that case, maybe you want to refactor to make it more readable from the human point of view, but it's still easy to test. Focus on context plus metrics for decision making. Again, context is everything. I think it's a difference for someone that aspires to be an architect or it's already architect. It's the context. You always take decisions based on the context. It's not, okay, I have 30 cyclomatic complexity, it's bad. No, it depends. It's legacy code. Okay, it's bad, but we cannot do nothing. Let's create a task and the rest is in the future. Let's go this step by step. Let's not call it a bad thing. It's a challenge, let's say like this. Okay, always take into account the context. Tools to measure, if you want a list here, SonarQube is quite popular for these things. PMD in Java, check style, can help in some complexity checks, but maybe PMD and SonarQube. SonarQube, it's the guys that invented, for instance, the cognitive complexity. JavaScript and TypeScript, you have ESLint, Plato, in Python, and you can find on internet other tools. In C++, you have these ones, in C#, the Endepend, multi-language. SonarQube, it's multi-language. It's quite popular. You can use it for free if you're a project. It's not bigger. CodeClimate, Lizard, there are other ones more advanced, but SonarQube probably it's most popular for this kind of things, I think. And of course, using CI to enforce thresholds and track over time. I always use these. I create dashboards, I send emails to the teams and say, okay, please check your code. That's a way. It's better than try to control the people. Just send them reports with these values. Put in red when they put, and people implicitly in their mind, they start to think, maybe I should change this. I don't like this red thing associated with my team or with my name. So in summary, cyclomatic complexity measures path complexity, helps predict testing effort, and maintainability should be used with other metrics that, like I told during this video, and target low CC for critical code paths. That's you should always target low as possible, but again, remember, in some contexts, sometimes it's not possible, and you have to understand what are the constraints of the project, the context, how, like the example, as I said, we inherit a project. It's not on our side to avoid the complexity or the number of tests, things like that. It was just, it is what it is, right? So further reading, if you want some reference, there are a lot of more, but Sonar Cubes, it's a good reference. They really have good helps for all the metrics. Martin Fowler, Refactoring, it's a great book. I bought it, to be more accurate here, when the second version, I think it's targets JavaScript. There is also a first version, but the second version will follow. I think everything is in JavaScript, and you can learn a lot from it. And of course, this is the article from the McCabe here, and there are of course the tools that you can always find. They usually have some explanations about the metrics. So thank you for this video. I hope this video was useful. I thought that I brought some innovation to you. Sometimes people say, I already know that metric. Okay, but I hope that I brought to you some insights that probably you never think about. Remember that my channel, it's about architecture. I was a developer and I still develop things, by the way, a lot. I really like to develop, but I usually like to teach people about the, let's say, the scientific and management part of being a software engineering. It's not a technical person. It's more than that. It's like the other professions where you have the technical part, but you have the scientific part. At the end of the day, we are kind of a scientists, but unfortunately, we only discover that after 10 or 20 years when you are in this business. Again, thank you for watching this video. Please subscribe, share it with your friends. Comment. I always read the comments and sometimes I answer to them. There was a guy that asked me to create a video about micrometer, I think, and I created. It was a great experience, and I don't mind to, if I have time, to provide that to help you to be better. And of course, I don't want to be just saying the guy that I'm giving things. Of course, I learned a lot, to be fair here, when I'm developing these, because I remember all these things. I go into details. It's always great. And as usual, I'm talking too much. And again, so thank you for watching, and I hope to see you in my next videos.